Good afternoon, class. Today we're going to be looking at inverse functions. And I need to do a little writing first. Let me turn on the camera. There. And let me shrink this down there. As we'll recall, a function we said has no repeated x value. A function, no repeated x value. A one-to-one function. Here's something that's new. A one-to-one.
New to thing.
New to y'all. New to the class. One-to-one function has no repeated y value. Now, since it's a function, it has no repeated x value either, but what's new here is that we have no repeated y values if the function is one-to-one. No repeated y values. And let's look graphically. What would that mean if we take a graphical interpretation? Let's look, something, I'm going to make up an example before we do look at problems 1 and 2. Here and here. There. And I think I will ready. Okay. How about a parabola? A parabola opening upward, a quadratic function. Remember, for a function, use the vertical line test for that, okay? So I think we can look and convince ourselves that this is definitely the graph of a function. For a function, use the vertical line test. Y'all remember that? Okay, good. Use the vertical line test. And we can see, yes, this thing is definitely a function. But what about being one-to-one? Do we have any repeated y values? Let's look at these 2 points right here. Let's look at these 2 ordered pairs, here and here. Well, I don't know what the x value is, but based on where that point occurs, we know the x value is positive. What's the y value? Zero. The y value would just be 0 because it's sitting on the x-axis. What about this point? It would have a negative x value and a 0 for the y value. So what do y'all think? Is this one-to-one? One-to-one can't have repeated y values. It's not one-to-one. We just found repeated y values. Repeated y value. So not one-to-one. In general, we have the vertical line test to determine if a graph is a function. We have the horizontal line test to determine if a graph is one-to-one. Imagine, even if it weren't passing through that x-axis. I'm going to draw it. You're right. Can you draw a a horizontal line so that it hits the graph twice? If so, right here and here, those points have the same y value. So for vertical line test, we use that. For the functions, to determine if a graph is a function, we use the vertical line test. If we're going to determine whether a graph is one-to-one, we're going to have to use the horizontal line test. So, let's look at problem number 1. Okay, this is number 1. And I'm going to draw a picture. Yeah,
It's a slanted line.
It's a slanted line. It looks like, let's see, the numbers on the X and Y don't matter. It's a slanted line. Okay. Oh, so here it is. Let me put on the arrowheads on the X and Y axes also. There. What do y'all think? Is a slanted line 1-to-1? This is a yes/no question. Is this graph 1-to-1? Can you draw a horizontal line so that it hits it twice? No. So any slanted line, whether it's rising or falling, any slanted line must be 1-to-1.
Just like, what about a quadratic function, one of these parabolas?
This was a quadratic function, a parabola. It doesn't matter whether that parabola. Well, let me finish writing this sentence here, this statement. Any slanted line is 1-to-1. It doesn't matter how. If it's rising or falling, it's still 1-to-1. What about a parabola? Suppose the parabola had been opening downward. Would it be 1-to-1? No, it doesn't matter. Quadratic functions are not 1-to-1. So I think I'll say parabolas are not 1-to-1. So go to number 1.
Just yes, no. Is it 1-to-1?
Is it 1-to-1? And what did y'all say? Yes?
Oh, I said yes.
Okay.
They said yes.
Yeah, they said yes too early. Okay. Now this next one, let me draw a picture of it. Okay, this is number 2, and let me try to show you that for a moment people think that graph is going to change directions, but it isn't going to change directions. If it were going to change directions, they would have shown it more clearly. It is going like this. It's going down. It's switch over here to my.
Not.
This thing, for some people think, it's going to turn around. It's a parabola. No, they're trying to show that it's just a gradual decline. Okay, a very gradual decline. What do y'all think? Is that graph 1-to-1? Yes, no matter where you draw those try to draw that horizontal line, it's not going to hit in 2 spots. So yes, this is 1-to-1.
Now this doesn't have a name like a slanted line or a parabola.
No, there's no nice name there. Just a curve. Any
Yes.
questions there? No, don't go on to that.
Okay. See all these horizontal
Look at all those
lines.
horizontal lines. None of them hit the graph twice.
Mm-hmm.
Okay, so yes, it is 1-to-1.
Just yes, no. I hope there's a lot of them.
No, there aren't. Well, there are still. Once I talk some, problems 3, 4, 5, 6, and 7 will be very quick. But I have to do a little talking first.
You always got to do some talking.
Okay, so let's summarize, okay, with regards to 1-to-1. This 1-to-1. If you're looking at a graph, then use the horizontal line test
To determine if it's 1-to-1.
If you're looking at just a set of ordered pairs, 1-to-1 means there's no repeated y values. So if they give you a set of ordered pairs and you're trying to decide, are they 1-to-1, just look at the y coordinates. Just look at the y coordinates for ordered pairs. For ordered pairs, just look at the ordered pairs. Just look at the y coordinate. Just look at the y coordinates. If there's a repeated one, then I'll say the y values. If there are repeats, then not 1 to 1. The third thing, equations. That's how we work with functions most frequently, or equations. So, how can we determine if a function written as an equation is 1 to 1? What would create those repeated y values? Think about a parabola. A parabola has to have what term? We say it's a quadratic function, which means the equation must have what appearing in a term? X squared. It's those even exponents. The same thing that causes all the problems. If a cut point problem, does it alternate, or if let's see, that's what happens with why we wind up with those imaginary numbers. The way even exponents take negative things and change them to positive things. And so it's the x squared. Those are things you need to look out for. Okay. For an equation, what would not be 1 to 1?
Even exponents.
Not 1 to 1. If you're looking at even x, if your equation contains even exponents, in particular, things like x squared, x to the fourth, and so on. Suppose we were looking at a cubic. Suppose we're looking at a cubic. A cubic has an x cubed. Would that be okay? Yeah, that would be fine.
We drew cubics. It was a little squiggly drawing.
Remember, it was a little squiggly like that.
We had a
now, if it had an x squared stuck in it, then if it's just in y equals x cubed, then it's going to be 1 to 1. Now, if it's something like, don't bother writing this down, this is a throwaway. If it's something like x cubed minus 7x squared plus 5x minus 1, oh, I'm betting that x squared right there, what would you say? You're probably not going to be 1 to 1. Okay? If your equation contains even exponents, probably not 1 to 1. There's something else. I remember looking at something else that took negative quantities and changed them to positive quantities. They even had a little graph that was reminiscent of a parabola. The graph looked like a little V shape. What? Oh, there it is. Absolute values. Absolute values. It fails that horizontal line test. So if your function has absolute values, then you're not going to be seeing, it's not going to be 1 to 1. Absolute values, not 1 to 1. And that'll be important towards the end of the class. Right now it's not that significant, but okay. The name of this section is inverse functions. Loosely speaking, an inverse just swaps the x and y coordinates. I'm going to write it down here. An inverse swaps x and y coordinates. I think I'll just write swaps x and y. All you're doing is just swapping the x and y coordinates. For example, here I have a couple of examples for you, okay? That I'm just going to make up. There. I don't know what purpose this green thing serves.
I know, I told you the other day we should.
Let's just try it. What do you think? There.
Oh, I like that better without all that green.
Oh,
around.
I don't know. I think it's too white. What do y'all think? I think there's a glare. No? Yes? Does it not matter to you?
They don't care.
They just want me to go. I dangled that. We're going to finish early today in front of them, and now I'm just going as slow as I can. Yes, okay. Yeah, I think it's better. I think there's less glare with the green. Okay, let's consider these two functions. Consider f and g. I'm giving us two functions. Okay. Function f. Now, I'm going to make it with just three ordered pairs, okay? Let's say 0, 9, 1, 7, and 3, 4. And I'm going to skip a line. And I think you'll agree this is a function. Notice there's no repeated x values. So f is a function. And here's another one, g. It has ordered pairs 0, 3, 2, 4, and negative 2, 4. Now in terms of functions, hopefully you'll agree both f and g are functions. There's no repeated x values. So both of these things are functions. I'm going to write that down. Consider f and g. Both are functions. An inverse swaps the x and y values. We have a special notation for inverse function. Now save us some writing. It's the name of the function with a little superscript of -1. It looks like f to the -1 power. Raising a function to a power is meaningless. If you see a function name with a little -1, that's our algebraic, that's our shorthand for saying the inverse of f. The inverse of f. You're just swapping x and y, so 0, 9 becomes 9, 0. 1, 7 becomes 7, 1. 3, 4, what order pair is that going to become? 4, 3. So there's f inverse. Let's write out g inverse. Which ordered pairs are in g inverse?
I'll get them going. 3, 0.
0, 3 becomes 3, 0. 4, 2. And 4, -2. We started off with two functions. F is a function, g is a function. We formed their inverses. Look at the inverse. Is there repetition among the x values for f inverse? 9, 7, and 4. No, there's no repetition, so f is a function and f inverse is a function. But I think we have a big problem with g inverse. G is a function. We said 0, 2, and -2. G is a function. What about g inverse? It is not a function. Why? What number's the problem? That 4. We now have repeated 4s. So g inverse is not a function. Well, what went wrong? Both of them started off as functions, but when we formed the inverse of f, it was a function. The inverse of g was not a function. The difference is that f is 1 to 1. That is 1-1. That's an algebraic notation for 1 to 1. F is 1 to 1. Was g 1 to 1? No, we have those repeated 4s right there. And it's fine to have those repeated y values. That's fine. G is still a function. But when you reverse it, what's happening here? The x's in the original problem are becoming what? And the y's in the original become, and there it is. Those repeated y's, that's fine. But when we flip the ordered pairs, we have repeated x's, not a function. What's important here is that only one-to-one functions have inverses that are functions. You can still find the inverse. It's just not going to be one-to-one.
And not a function.
It's not going to be a function. Only one-to-one functions have inverses that are functions. And that's important because if it's not one-to-one, they're not going to want you to find the inverses. We go through the homework. If the thing isn't one-to-one, you're just got to state not one-to-one. You won't actually find the inverse. And there's one other thing. While I'm here, we may as well mention this. Looking back at f, we're still working with the function f above. We're still working with function f above. If I wanted you to tell me the domain of f, what numbers are in the domain of f? There's only 3 of them.
0, 1, 3.
Okay, 0, 1, and 3. Now look at that inverse. Look at that inverse. Where is 0, 1, 3 in the new function f inverse? The x's in the original became what? The domain values in the original became y's. So what do you call those y values? The set of y values is called the range. So the x's in the original become the y's in the new. So the domain of f is equal to the range of f inverse. Let's apply that same logic now to the range of f. Looking at the original function f, what numbers are in the range?
I'll get them going. 9,
7, and 4. Look at the new function, the inverse. 9, 7, 4. They started off as y's, but what do they become in the new function? They became the x's, and we call the set of all x values the domain of f inverse. Hopefully you'll follow my logic, and hopefully it makes sense. The x's in the original became y's in the new. The y's in the original became x's in the new. Any questions there? Look at number 8 in the homework.
Oh, number 8.
Mm-hmm.
Oh.
The domain of f is equal to the blank of f inverse. And you have a pull-down menu. What are you going to choose? The range, okay. The range of f is equal to the domain of f inverse. And they tell you some gobbledygook there, saying, well,
the x becomes a y.
And the y became an x. Okay.
Right.
Okay, let's go back to number 3. Determine whether the given functions are inverses. Here they're not listing them as ordered pairs, they're writing it as a table, but
you can sort of see
you can still see the ordered pairs. Let's look at that first table. This is something we can answer without showing any work. Just look at the problem. -1, 2. If G is the inverse, it had better become 2, -1. Is that what it became? X, Y, okay. What about 2, -3? What did it become? -3, 2, yeah. What about the third one? Negative 3, 5. What does it become in the new function? Or what should it be in the new function if it's an inverse? It should be 5, negative 3. What have we got there? That's a negative 5. So are these inverses? Did they just reverse those ordered pairs? No. Do y'all see the problem? It's the third row of the table. Negative 3, 5 should have been 5, negative 3. Instead, they made a negative 5, negative 3. So the answer is no, they are not inverses. Number 4. Are these functions inverses? Let's look at these functions. They're giving them just as ordered pairs here. This is nice. What do y'all think? Are they inverses of each other? Yes, yeah. It looks like they're just switching them. Look, negative 2, negative 6 became negative 6, negative 2. 2, 3 became 3, 2. 3, negative 2 became negative 2, 3. And 8, 11 became 11, 8. And so, yeah, I'd say yes, those are inverses. They're just swapping the ordered pairs.
Oh, you'll notice it's final check if you...
Because there's only 2 possibilities. If you get it wrong on the first one, you're going to have to get a whole other problem. With only 2 possible answers, they're not going to give you a second shot to correct your mistake. Next. Okay, let me write this one down.
I remember once having this problem on a test, and every student in the class missed this problem. It was years ago, before we moved to this new building. Students are smarter now.
2020. Okay.
I don't think this is the one that was the other one.
Okay. If the following defines a one-to-one function, then find its inverse. If it's not one-to-one, you select not one-to-one. They don't want you to find the inverse of a function that's not one-to-one. So let's look at this problem number 5 first of all and decide, is it one-to-one? Yeah, I wrote it down. Is this thing one-to-one? What do we look at to decide if it's one-to-one? The y values. Negative 18, 8, and 20. Are there any repetition? Is there any repetition there? Any repeated y values? No, so this is one-to-one. It is one-to-one, so we have to find the inverse. We just flip the ordered pair, negative 18, comma, negative 8, 8, comma, negative 13, and, well, 2020. Just stays 2020. And this is multiple choice, so it's not D because it is one-to-one. Negative 18, 8. 8, negative 13. I think it's, what are y'all getting? I'm getting A.
The first one?
Mm-hmm.
Negative 18, negative 8. Yeah, A. I think it was the next one that I had to test and everyone missed it.
That sounds to me like your pedagogy was failing you there. Mm-hmm. Okay, so we have negative 15, 10. Same instructions. If it's one-to-one, find the inverse. If it's not one-to-one, select not one-to-one. What's with this 19, 19 and 20, 20? Huh. Okay, switch over. No, it isn't tricky. It isn't
Read
tricky.
the instructions once again. If it's one-to-one,
find the inverse. If it's not one-to-one, select not one-to-one. Is this one-to-one? It is one-to-one?
Are there any repeated y values?
If there are repeated y values, then it is not one-to-one, okay? We have a repeated 10 as a y value. We have repeated y value, so not 1 to 1. We have a repeated y value, so not 1 to 1. Any questions there?
That's what you choose. Why did that class mix? What do y'all think the class did wrong that time that every student got it wrong?
They chose A.
Yeah, they chose A. But y'all see why we're not switching the X and Y's?
If it's not 1 to 1, do not find the inverse. We only want the inverses of 1 to 1 functions. What about number 7? Same instructions. Y'all think y'all can do this without me writing down anything? I'll rest my arthritic fingers. Okay.
Is it 1 to 1? Look at the Y's. Are there any repeated Y values?
No repeated y, so it is. You see, I always like it when it's not 1 to 1 because you just say not 1 to 1
and stop.
Yeah, and stop. But here we're going to have to reverse these things. A, B, C. Which one? I think it's B. The -2, 3 became 3, -2. -4, 15 became 15, -4. 2, 5 became 5, 2. And -1, -6 became -6, -1. And check our answer. Now we've already done number.
Let's just make sure there's no questions. Why is number 7 different from number 6? Why did we not switch the X and Y on number 6? Because the way it says, if it's not 1 to 1, you write not 1 to 1.
And I think we've already done number 8. Show them number 8. Remind them of this important concept.
Domain of F is equal to the range of F inverse. Range of F is equal to the domain of F inverse.
We don't spend a lot of time finding ranges of functions. We're more interested in the domain of functions. And here's a strategy to find the range of a function, find the inverse, and then use your domain rules. We're going to have a process for finding the inverse of a 1-to-1 function. So if you ever needed the range of a function and you don't have the graph to look at it, then find the inverse and apply your domain rules. Okay, number 9. Oh, this is good here. Let me write this down. Okay, f of -3 is equal to 6. They tell us that f has an inverse and that f of -3 is equal to 6. Then f inverse of 6 is equal to blank. Look at this initial statement here. Remember, the number in the parentheses, that's the x. The value of the function, that's the y. So we have -3, 6. With the inverse, all of a sudden, 6 is the x value. What would the y value have to be? Pardon me?
-3.
-3, that's right.
All you did was
Reverse x and y.
Oh, let me type that in.
Oh, thank you.
-3. Good job.
I was outside almost all day yesterday in this dirty air. Same thing with my brothers.
Are you going to talk before we do this?
You'd probably like it if I did. I guess I
Are you going to
will.
tell them something before we do too?
Yeah, I will. Okay. Let's assume f and g are 1-to-1 functions.
Why are you
I think I said something to you that is how we talk to each other when no one's around.
Or one-to functions.
Or one-to-one functions. But normally I wouldn't say. You'd probably like it if I did. I wouldn't say that to you normally. I don't know where that came from. Okay. You asked, are you going to talk some first? And then I said that. What did that mean?
I have no idea.
Your tie is crooked also.
Oh,
Oh, now that we've started these ties, it was hot today. I didn't want to wear
but
this
that's
thing.
the first step to taking over the world.
Yes, that's right. I've got to look professional if I plan to take over the world one day. Okay, let's go back. Let's assume f and g are one-to-one functions. This is the formal definition of inverse. F and g are inverses if each of the following is true. Each is singular, so is true. First one. There are two conditions. If they're both true, then we can be certain that the two functions are inverses. F composed with g of x is equal to x for every x in the domain of g. It's ringing some sort of bells. And then the second condition, if we reverse the order of the functions, g composed with f of x, that's also equal to x for every x in the domain of f. If you find the composition in both directions and everything except the x cancels out, then you can be assured those two functions are inverses.
I'm going to look for something. I think
I recall we did something the last homework assignment.
No, not
yeah. It was it was a review.
Oh, a review. Okay.
For the zeros. But let's see. Come back over here. Don't y'all remember something where? Oh, don't tell me I closed something I shouldn't have. Oh, that's okay. Here. Oh, we get into white error. White label error. Okay, where is it? Where's the stuff we were just doing? No, let's see. There it is. It's composition. Do I remember these problems here?
That's what I said. Find it.
Oh, you mean to find it in the work? Okay.
Everything starts canceling out.
Do I remember these problems here? Here's number 11. We'd find f composed with g. Remember the way we would plug in, and then everything started canceling out. The cube root of x cubed just reduced to x. And when we go in the other direction, that cube root and cube canceled out. Multiplying the 9 by the 1/9 canceled out. We subtracted out the 4/9. Everything canceled out except for the x. In this event, we can say, and then ask, are the compositions equal? And we said yes. We can say something else now. F and G are inverses. If you started plugging in x values to create y values in F, the ordered pairs for G would be exactly the opposite. And before we go on, where are we? Let's think about it. I'm going to draw an abstract illustration involving this definition. Those aren't eyes. 1, 2, 3, 4. Let's assume that F takes 1 to 3 and 2 to 4. We're looking at this little mapping, and there's two ordered pairs, 1, 3 and 2, 4. If G were the inverse, if G were the inverse, G would have to take 3 back to 1 and 4 back to 2. With our intuitive notion of inverse, we see that F and G are definitely inverses just because the way we're reversing the ordered pairs. But what is this definition saying? This definition says it doesn't matter where you start. If you perform the two functions consecutively in either order, you're going to end up where you started. If I start at this 4, let's perform the two functions. 4 goes to 2, 2 goes back to 4. You're ending where you started. Suppose we had started at 1. 1 goes to 3, 3 goes back to 1. When you perform the two functions consecutively in either order, if they're inverses, you will always end where you started. Is that clear? That's what this thing is saying.
Like if you were driving from your house to the school, the inverse would be going the other way, going from school back home. If you drove here, then drove home, you're starting and stopping at the same spot.
Well, let's suppose we had a mapping that's clearly not swapped ordered pairs. I don't like that. Oh, let's see. I guess I'll leave F the way it was. F will take 1 to 3 and 2 to 4. Now let's suppose G takes 3 to 2 and 4 to 1.
Oh, this is a good example for illustration.
No, I couldn't tell if you're being facetious. Oh, okay. Let's suppose if they're inverses, I think we already know our intuitive notion, an inverse swaps ordered pairs. Is this mapping swapping the ordered pairs? Is it reversing the ordered pair? No? Well, let's see. Will we end up wherever we start? Let's just start at 1. 1 goes to 3. 3 goes to... Does it go back to 1? 3 goes to 2. You're not ending where you started. So these are not inverses. If we had started at 4, inverses. I will. Okay. 4 goes to 1. And then where does 1 go? To 3, you don't end where you started. So these are inverses. These are not inverses. When we get to exponential and logarithmic, we're going to be saying logarithmic and exponential functions to the same base. When they're performed, they're inverses, and when they're performed consecutively in either order, they're going to cancel out everything, leaving you where you started. And that's what these illustrations are trying to show. In order to be inverses, if you perform the two functions consecutively, you have to end where you start. Okay. Let's look at number 10. They give us two functions.
Oh, wait. I got to get out of here and go back.
Yeah, that's right. This is number 10. I'll go back to the new assignment.
Inverse functions.
Yeah.
Oh, by the way,
number 10.
My Canvas classes have had trouble syncing. A student had taken a test weeks ago, and it still wasn't showing in the grade book on Canvas. And
there are certain students.
Yeah.
Let's see. Marissa left, but Marissa's first quiz would not sync to Canvas. I had to manually go take her grade from Pearson and type it into Canvas. If you notice that happening to you, you need to point it out to us, okay? But you have to give it a day or two. Canvas is slow at syncing, okay? But
it's not supposed to be.
It's not supposed to be. It's supposed to be. Well, why? Their recording is saying bad stuff.
Oh.
They're going to get... So we have f of x is equal to 9 over x minus 4. And we have the function g of x is equal to 9 over x and plus 4. Determine whether the two given functions are inverses of each other. Well, it's a yes-no question, but it's going to take quite a bit of work. If you have two functions and you're wondering if they're inverses, you have to find their compositions. F composed with g of x, well, it reduced to x in the other direction. So it's going to take a little work here. Here's something I'm noticing. I claim f and g are both 1 to 1. F and g are 1 to 1. Well, for equations, remember back here I said, where is it?
Even x.
For an equation, if you're trying to decide if it's 1 to 1, look at the equation. If they're even exponents, then then the thing isn't going to be 1 to 1. If they're absolute values, I don't see any even exponents. If that had been an x squared, then it's not 1 to 1. You wouldn't find that. You wouldn't. It's not they're not inverses. Even exponents are what causes all the problems. Even though people prefer even exponents over odd exponents. Let's get started.
So I think it works better.
There. Can y'all read that? Am I smearing it? Can y'all read that?
It's 9 over x minus 4.
Okay. We're going to do two things. First thing we'll do is find f composed with the g of x. Y'all remember that f composed with the g of x, that fog and golf stuff? I'll say it. F composed with the g of x. Remember that says take g of x and plug it into f. So we're going to take g of x and we're going to plug it in to f where there's an x. So we're going to have a 9 all over. In place of that little x there, what am I going to have? The red stuff, 9 over x plus 4. And we still have that minus 4 stuck on there. We took g of x and plugged it into f. Well, if they're inverses, everything's going to cancel out except for what? X? Well, one thing's disappearing right off. 4 minus 4. So all we have now is 9 over x. This is called a compound fraction, a fraction that contains additional fractions. There are two generally accepted approaches for simplifying compound fractions. What I like to do is multiply above and below by the minor denominator. This is the major fraction bar here, the blue one. Any fractions that appear within the major fraction are called minor fractions. Any denominators that appear in minor fractions are minor denominators. My minor denominator here is x. I'm going to multiply above and below by x. There's the major fraction bar. I'm multiplying above and below by x. This is working out nicely. Looking at this denominator right here, what's about to happen to those x's? I'm ignoring the top. Think of that x as an x over 1. What's about to happen to those x's? They cancel out. So we now have a 9x over x.
No, over 9.
Over 9, pardon me. And thanks. I have a 9x over 9. Let me write it here. 9x over 9. And what's about to happen? That's messy there. The 9's cancel, leaving us just x. So at this point, if I were running out of time and this were a test, I'd just guess, yeah, they're probably going to be inverses. Just because it reduces to x in one direction doesn't mean it will reduce in the other direction, but odds favor. If you were betting, it's an 80% chance. If one of them is x, the other one's going to be x. But we have time. Let's go and find the other direction now. Let's find g composed with f at x. You know what I'm going to have to do? I need to recopy f and g. F of x is 9 over x minus 4, and g of x is that 9 over x plus 4. We're going in the opposite direction now. We're taking f of x and we're plugging it into g. So we're taking f of x, here's f of x, we're going to plug it in to g. So we have a 9 over, in place of that little red x there, we're going to write the blue fraction 9 over x minus 4. But we still have something else stuck on out there. What is it? That red plus 4. Let me push this up.
You can't just cancel the 9s and leave an x minus 4 way down there.
It's a compound fraction. We have to get rid of the fraction within the fraction. Well, what's the minor denominator in this case? Earlier, the minor denominator was just x. What's the minor denominator now? X minus 4. We're going to have to multiply above and below by x minus 4. Looking at this denominator, the x minus 4s cancel. Now we have, so I'm going to write, it's messy, so I'm going to write what we have. We have a 9, we have an x minus 4, red 9 times blue x minus 4, all over, what have we got down here?
Blue 9.
We have that blue 9, and we still have that plus 4. Resist the urge to distribute that 9 over the x minus 4. If you do that, you then got to split it up and put each thing over 9 and cancel. The quicker thing is just cancel the 9s right there. Then you have that blue x minus 4 by itself. And what else do you have? You have that plus 4. And what's that going to leave us with? Just x. So now we are 100% confident f and g are inverses. F and g are inverses. A whole page of messy writing to convince ourselves that f and g are inverses. And before we go on, let's see. I'm trying to think of something that's okay. Okay, let's consider these two functions, f and g. If x is 5, we're looking at this blue function. Don't bother writing this down, just listen to what I'm saying. If x is 5, you're plugging 5 into f. 5 minus 4 is what? 1. So 9 over 1. The ordered pair 5, 9 is generated by that function f. That means if we plug in 9 here, if we plug 9 in for x into g, that would be a 1 plus 4. The y-coordinate is 5. These things, as ordered pairs are generated, if they're inverses, 5, 9 was one ordered pair, the other function had 9, 5. The ordered pairs are just being reversed. Any questions there? And that's just sort of a throwaway. I guess the sensible question is, if we have two functions, we can go through using composition, fog and golf, to show either yes they are inverses or no they're not. If both compositions reduce to x, they're inverses. If the compositions don't reduce to x, they're not inverses. So the sensible question is, how do you find an inverse when you're given a function?
Suppose you weren't told g of x equals.
How do you find the inverse of a one-to-one function? I'm sorry about that. I think that was my phone. I don't recall turning it off.
I turned mine off.
How do you find the inverse of a one-to-one function? This is a 4-step process, but it's easy steps. The first thing you need to do, if it's not one-to-one, they don't want you to find the inverse. You'll just have to say not one-to-one.
Why don't I show? So I think that's what you're going to say. Okay. Look at what we're doing on the next problem. Determine if it's one-to-one. Find a formula for its inverse. So you're going to come up with a little formula that's the inverse of this. Okay? Keep talking to me.
They should, let's see. Look at that function. The first step we're going to do in this process is we got to verify that the function's one-to-one. Switch to my paper. I'm going to write down that first step. You got to verify, just convince yourself that the function is one-to-one. Because if it's not one-to-one, they're not going to want you to find the inverse. Verify that the function is one-to-one. And remember, I said, if you're looking at an equation, if it's one-to-one, there should be no even exponents. There should be no absolute values. So look at that problem.
Certainly no absolute values.
What about even exponents? I see an x. I don't see a power on that x. What's the assumed power if you don't see an exponent on a variable? 1, is 1 an even number? No. So this is one-to-one. So the first thing we'll do, we'll verify. Let's go ahead and select yes, it's one-to-one. And now I need to write out the steps for finding the inverse.
Okay. Now they want you to find that little formula. That'll be the inverse. Okay. Keep going, Tim.
Okay. Loosely speaking, what does an inverse do? What did I say an inverse does? When I first mentioned the word inverse today, I think I wrote out something. Where is it? Inverse? Inverse swaps x and y. And so, that's going to be, how would I say that? I think I'll say it like that. Swap x and y.
Literally, the variable.
Swap the variables x and y. At that point, you have a formula that's a form of the inverse, but it's not written as a function. So the third step, you'll have to solve for y.
That can be the part that's a little...
That's the part that can be a little tricky at times. And once you solve for y, God damn it. Did I say that? Did y'all hear me? Oh no, was it recorded? I need to do my cowboy cussing. Okay. Solve for y. And this fourth step, they've really done this step for you. My Math Lab, if you look at it, where's the mouse? There it is. Look at how they're setting up the answers. They've already typed the inverse function notation for you. So it's really just a 3-step process. But for the fourth step, I'm going to write, we'll replace y with f inverse of x. This is not a bad process at all, okay?
You want to go ahead and write down the problem?
Yeah, let's see, this is what number? 11?
11.
So f of x, was it 6 over x plus 3?
Well,
they want us to find f inverse. I'll just make a note of what we're doing there, or here. The first thing we looked and saw, there were no even exponents, no absolute value, nothing that we see could start generating repeated y values. So my first step, I'm going to say f is 1 to 1. I just convinced myself of it by looking at the formula for f. Now the second step, we have to swap x and y. Wherever we have an x, write a y. Wherever we have a y, write an x. Wow, I don't see a y in that problem number 11 either. What is acting like y? What's a fancy way of saying y? The f of x. F of x is the thing that's acting like y. There, f of x is y. So in the second step, y becomes x, and x becomes y. Did y'all follow my logic? F of x was a fancy way of saying y. Y became x, x became y. Third step, we need to solve for y. Solve for y. That means we need to get that y out of the denominator. Maybe we should write this as, I'm going to think of that x as an x over 1 and a 6 over y plus 3. What am I going to do now? Why did I write that x as x over 1? I don't think I'll bother multiplying by the least common denominator. What am I going to do here? We have an x over 1 equals a 6 over y plus 3. Cross multiply, yeah, that's what I'm going to do. Let's cross multiply. X times y plus 3, we're going to have to distribute that x. That'll give us I'll write it out, x times y plus 3 is equal to 6 times 1 is 6. We want to get y by itself. I'm going to get rid of those parentheses by distributing. If I distribute the x, I'll get an xy, what else, plus 3x. I'm trying to get y by itself. What will I do next to get y by itself? Not yet, no. Subtract the 3x. So we have xy equals 6 minus 3x. Now x times y, what are we going to do to get rid of that x on the left side? Divide by x. And that will give us y equals 6 minus 3x all over x.
Don't get carried away and cancel the x's.
That's not factored on top. Mm-hmm. You can't factor if you're not canceling. What you could do is you could split it up, 6 over x, and then cancel the x's to get a minus 3, but I prefer If my original function is written as a single fraction, I prefer the inverse to be written as a single fraction. I'm going to stop right here. We've just completed step 3. All of this was step 3, going through solving for y. But the last step, it says replace y with f inverse of x. So replace y with f inverse of x. And the answer is the step on that other side. To me, the fourth step is unnecessary. Once you solve for y, the step on the other side is the answer you're looking for. MyLab already does that, replacing y with f inverse of x for you. All you have to do is type in what you have on the other side of y. So f inverse of x, what's he going to click first? To type in
6 minus 3x over x.
What will he type in first? Which, let him look at my answer again. What's he going to, for this thing here, what's he going to click first?
You're asking is, how do you type in this fraction?
How do you type in this answer? The first thing you have to use is the fraction bar. And then on top, 6 minus 3x. And on bottom, just an x. Any questions there?
So swap x and y, solve for y.
Mm-hmm. Once you verify that it's 1-to-1, it's really just a 2-step process. Swap your x's and y's, and then solve for y. Let's do another one, number 12.
Well, the plus side is that there's no fractions here.
F of x is equal to x cubed minus 7. Determine whether the function is 1-to-1. If it is, find its inverse.
I remember one semester a student saying, with such great confidence, it is not 1-to-1 because there's an exponent.
I didn't say it wasn't 1-to-1 if there were exponents. I said it's not 1-to-1 if there are, what sort of exponents? Even exponents. When we look here, I don't see an x squared or an x to the fourth. I see an x cubed, and that 3 is an odd number. So what do y'all think? Was that student of Tony's right? This function is 1-to-1. They're not going to let you get away with saying not 1-to-1 because then it's over. Then the problem's over. So some of those easier ones where you're just listing the ordered pairs, okay, they'll not be 1-to-1. But for these formulas, they're going to want you to find the inverse. And so the first step, f is 1-to-1. We've convinced ourselves of that. Then the second step, we have to swap x and y. What's acting like y? F of x is acting like y, so y becomes x, and x becomes y.
Step 2 is pretty easy.
Yeah. Step 3 is the only one that requires, some work. And even here, it's not that bad. We need y by itself. There's only one sensible next step. What is it? Add 7. That's right. Get that y cubed by itself. So you have x plus 7 is equal to y cubed. Well, we have a problem with that cube. What are we going to do to get rid of that cube?
Cancels a cube.
I couldn't hear you. Cube root. Okay. We're going to take the cube root of both sides. I'm going to take the cube root of both sides. The cube root of y cubed reduces just to y equals the cube root of x plus 7. And there it is. Here's the formula they want for the inverse. You don't have to write out f inverse of x equals, because MyLab is going to do that for you. Once you get y by itself, the step on the other side is the inverse. Any questions there?
Type it in. Click here.
Okay, don't use the square root hot button. Notice he's using the one that has the 2 blue boxes. For up there at the index, you have to type that 3, and then underneath it, x plus 7.
Oh, just x plus 7. Okay.
And any questions there?
So interchange x and y, solve for y.
Look back and make sure that's the last of the new material. I don't know what number 13 is, but I think it's old material. Completing the square to find the center and radius of a circle. Yeah.
Look, flip through everything we did today. Is there any questions on this? Some of the problems, the early ones really weren't that hard.
Well, nothing was that hard, I hope, compared to what we've done. Say solving square root equations and stuff.
More that
None of this
is,
yeah, that's a mess, isn't it? Any questions here? No? Okay, I'm going to stop recording.